All right, today we're diving into a really huge breakthrough in artificial intelligence. We're talking about a new kind of AI that might finally be able to tame chaotic systems, the most unpredictable forces in the entire universe. And what that really means is we're talking about an AI with reflexes. But, that brings up a massive question, doesn't it? How on earth do you even begin to control something that is, by its very nature, designed to be uncontrollable? Something where what happens next has almost nothing to do with what's happening right now.
Okay, here's probably the best way to think about it. Imagine you're trying to steer a tiny ship in the middle of a Category 5 hurricane. The waves, the wind, everything is working against you, trying to throw you off course. And every tiny move you make has these massive, totally unpredictable consequences. So before we can even get to the solution, we've got to understand the enemy. Let's really dig into what makes chaos, well, chaos.
And here we go. This is the absolute heart of the matter. You see, chaos isn't just random noise. It's actually deterministic, but it has this extreme sensitivity to where it starts. We've all heard of the butterfly effect, right? A butterfly flaps its wings over in Brazil, and that teensy tiny change in air pressure somehow spirals into a massive tornado over in Texas. That's chaos. The smallest, tiniest nudge, and you get a completely different universe. Okay, and here's where it gets really, really tricky. There's a ticking clock, a really strict one. It's called the Lyapunov time. Think of it as your absolute window of opportunity. If you hesitate, if you're even a fraction of a second too slow, poof, your chance is gone. The system is already morphed into something else, and your action is totally useless. Or even worse, it could actually make everything blow up. Now, you'd think, hey, we've got these super powerful modern AIs, right? This should be easy for them. Well, nope. Turns out chaos is like AI's kryptonite. It's its one big blind spot.
And this slide just lays it out perfectly. It's a total mismatch. Your standard AI, the kind that's all over the news, it's like a really careful, book-smart student. It needs tons of time and mountains of safe, clean data to learn anything. But chaos? Oh man, chaos is the exact opposite. It's a pop quiz every millisecond, and there are no do-overs. The data you get is dangerous, and trying again is expensive. So why does deep learning fail so hard here? It really comes down to two big problems. First, what's called inference latency, which is just a fancy way of saying it's too slow. By the time the AI figures out what to do, the moment has passed. That baseball analogy is perfect. It's like swinging the bat after the catcher already has the ball. And second, it is just so data hungry. It needs millions and millions of practice runs. You just can't do that when you're messing with a fusion reactor, right? The stakes are way too high.
Okay, so the old way is a complete non-starter. We need a totally new playbook. And this is where things get really, really cool. This is where we get reflexes meeting reasoning.
The genius move here was to stop trying to build one single AI that could do it all. That's not how we work, right? So the researchers looked to the best system out there for inspiration, our own bodies. And this is the setup. Think of it like an AI with a body. You've got the brain. That's your standard reinforcement learning AI. It's the strategist, thinking about the big picture, the long-term goals. It's smart, but, a little slow. But then you've got the reflex. This is the new magic ingredient, the NGRC. It doesn't think, it doesn't plan, it just reacts instantaneously, and it's lightning fast. So what is this NGRC thing? Next Generation Reservoir Computing. Its secret sauce is pretty wild. It basically takes a ridiculously complex, messy, chaotic problem, and it transforms it into a simple linear puzzle, something it can solve in a single step. No guessing, no thousands of tries, just one shot, one answer. That's the key to its insane speed. Just how much more efficient are we talking? Well, this number, it says it all. 1/50th. The new hybrid system needs only 1/50th of the data to learn compared to a normal AI. That's not just better, that's a whole new paradigm.
Okay, the theory sounds great. It's elegant, but does it actually work in the real world? Let's get to the proof. Let's see what happened when they unleashed this thing on some of the most notoriously chaotic systems we know of.
First on the list, the Lorenz system. This is like the final boss of classic chaos theory. It's a mathematical model of atmospheric chaos, the one that gives you that iconic, beautiful butterfly shape.
And the challenge? They tried to force it to stay perfectly still on a single, incredibly unstable point, like trying to balance a needle on its tip. And the result? You're not going to believe this. 10,000 times. The new hybrid AI was 10,000 times more accurate at controlling it than the old AI was. I mean, that's not just a little better, that's a different sport entirely. All right, but that's a math problem. What about the real world with real consequences? Well, the next test was about as high stakes as it gets, controlling the insanely hot volatile plasma inside a tokamak fusion reactor. We're talking about something hotter than the sun, where things go wrong in microseconds. One mistake, and it's not good. But you know what's really mind-blowing? It's how it did it. The AI didn't just fight the chaos. It didn't use brute force. The researchers said it learned to surf the system's own chaos. Think about that. It was making these tiny, almost imperceptible nudges at exactly the right time, using the system's own wild energy to gently guide it back to where it needed to be. It's just beautiful. So look, these results, they're not just small steps forward. This is a signpost pointing to a totally new future for robots, for drones, for everything autonomous. A future that's agile. And it all comes back to speed. On the right kind of chip, this NGRC reflex is 75 times faster than a deep learning model. We're talking about the difference between nanoseconds and microseconds. That might not sound like much to us, but in the world of physics, that is the literal difference between success and catastrophic failure. But this crazy speed isn't just for showing off. It unlocks a brand new power, resilience. True resilience. The ability for a machine to adapt on the fly to something going terribly wrong. For example, imagine a drone flying along and bam, one of its propellers gets damaged. Okay, so this is how it plays out. The propeller gets hit and the drone's entire physics change, right? Instantly, the NGRC reflex feels that something is wrong. In milliseconds, it updates its own understanding of how the drone flies now. That new world model gets passed up to the RL brain, which immediately figures out a new strategy to stay in the air. And just like that, the drone stabilizes itself. No human intervention, no going back to the lab for retraining. It just adapts. That's the dream right there. So at the end of the day, what we're really talking about here is way bigger than just a smart algorithm. This is a fundamental shift in how we build AI. We're moving away from AI that starts as a total blank slate to what you could call physics-aware AI, an AI that has an intuition for the laws of the universe baked right in. It understands the grammar of the real world from the get-go. And that leaves us with one last, huge question to chew on. For decades, our machines have had brains, but they've been clumsy. They've lacked that split-second physical intuition that we humans just take for granted. Now, for the very first time, we can actually give them reflexes. So the question isn't if this changes things, it's what are we going to build with it?